Okay, we talked about global warming and cyclone and talked about the difficulties of attributing the changes in number of cyclones, intensities, rainfall increases, tracks, propagation speeds, and so on to global warming. But the exceedance rates, as shown by Kosin et al., who is one of the co-authors here, that the number of cyclones that reach higher categories 3 to 5 on Saffir-Simpson scale, let's say, is detectable, and there are some attribution studies, especially the ones that use explicit convection, to argue that this is relatable to the anthropogenic forcing and warming caused by that. There are nice papers by Kerry Emanuel, the first one from 1987, about how warming can be explained in terms of the Carnot cycle, the difference between surface warming and the upper tropospheric warming, and the integrating Bernoulli's equation going from the outer edge to the inner eye, maximum sustainable pressure, potential intensity, and so on. He also has a paper in 1999 arguing about warming and the thermodynamic processes which should give us intensification rates by increasing the enthalpy exchange with the ocean, right? Because the difference in ocean warming and the atmosphere should drive more energy into the cyclones. This study looks at the recent increases in tropical cyclone intensification rates. Let's read the abstract and then add some details. So tropical cyclones that rapidly intensify are typically associated with the highest forecast errors, that's not good, and cause a disproportionate amount of human and financial losses. Therefore, it is crucial to understand if and why there are observed upward trends in tropical cyclone intensification rates. Here we utilize two observational data sets. Not good news when you have to use two, and why there are two. To calculate the 24-hour wind speed changes over the period 1982 to 2009, we compare the observed trends to natural variability in bias-corrected, high-resolution, global coupled model experiments that accurately simulate the climatological distribution of tropical cyclone intensification. So the model, it's called high floor, high resolution, forecast oriented, low ocean resolution, coupled model global, which is computationally optimized to capture hurricanes by atmospheric processes while reducing computational cost by keeping the ocean at a lower resolution, and establishing its credibility in terms of the intensification, climatological distribution of intensification, so that attribution experiments can be done with warming. And they do different decades, 1940s and then maybe 70s and the present decades. Both observed data sets show significant increases in tropical cyclone intensification rates in the Atlantic basin that are highly unusual compared to model-based estimates of internal climate variation. So we need to know the baseline of what we expect from natural variability of intensification rate changes, so that the detected increase in intensification rates can be then examined for attributability. Our results suggest a detectable increase of Atlantic intensification rates with a positive contribution from anthropogenic forcing, and reveal a need for more reliable data before detecting a robust trend at the global scale. So the data sets used, IB-TRAX and ADT HERSAT, we looked at this before in the context of Kosin's paper on exceedances, the number of cyclones that reach higher categories compared to the total cyclones, and the trend in those in each cyclogenetic region. Here we are looking at global slope in knots per year, so intensification rates, and quantiles going from 0.05 to 0.95, and Atlantic. Atlantic is where there is more data, and the two data sets are closer to each other, so confidence of the understanding of processes and trends is established in the Atlantic, and then it's obviously necessary to explore the global trends as well. You can see that there are larger differences in the global trends of intensification rates. So this is the quantile regression of 24-hour intensity changes. Slope of the quantiles for 24-hour intensity changes during the period 1982 to 2009 for IB tracks and ADT, going from 0.05 to 0.95. And these red lines here are showing the trends as measured by ordinary least square regression, and red dotted lines show 90% confidence intervals, and this is here the 90% confidence interval as well. So in the Atlantic, there is high confidence from both data sets that there is a recent 24-hour intensity changes. So that establishes that the signal is detectable. And the slopes can be looked at in terms of number of rapid intensification cases to the total cases from the two data sets. Again, for the Atlantic, where they are remarkably in good agreement with each other with the slight difference in the slopes. And for the global, the differences are larger, but the upward trend is clear in both data sets. Okay, that's what the caption says as well. And I'm not going to show the model experiments, but they do model experiments with the global model for different decades with lesser of a warming signal in the ocean in the 1940s, and then more several other decades after that where warming is more detectable and has global patterns. And essentially the conclusion of the paper is that indeed there is a detectable increase in rapid intensification cases in the Atlantic, and as I mentioned also in the Indian Ocean. And in fact in the Indian Ocean, the 2021 pre-monsoon season had one cyclone jump multiple categories from depression and deep depression to very severe and extremely severe cyclone in just 2 days, which was taking, over the last few years, it was taking 4 to 5 days. So multiple jumps. That's rapid intensification, but also happening multiple times during the evolution of the cyclone. Okay, so detectable signal in rapid intensification cases, and they can be attributed to warming, which in turn is attributable to anthropogenic greenhouse gas forcing. So this seems very clear now, and process understanding from such a model can help improve forecasts in terms of advancing predictive understanding as well. There are many papers which have looked at the processes of rapid intensification in terms of the subsidence in the eye that is enhanced. The warming associated with it is much larger, which feeds to the eye wall processes like convective bursts and so on, which help drop the pressure, increase the pressure gradient, enhance the maximum sustained winds, and give us this 55 km per hour jump in 24 hours, which is the official definition of rapid intensification, 30 knots or 55 kilometers per hour. Okay, I think it's about 15. It is 15 meters per second if I'm not mistaken, and 36 miles per hour and so on. So use all the units, but the story is that rapid intensification is happening. So again, the main message is that the changes have to be looked at in terms of intensification rates, potential intensities, propagation speeds, amount of rain, and stalling at the coasts and so on. So predictions have to improve in all aspects, but intensification rate prediction is very critical, because right now it is a great challenge for predictions, and prediction errors are higher when models miss the rapid intensification rates. And if more and more rapid intensification cases are going to occur, then prediction skill has to keep up and not lose the gains that have been made in the recent years. Okay.